Okay, starting the recording. We're going to look at another example here. It's a somewhat geometric example relating to partial derivatives. So let me give you a moment to copy this example down. Okay, so in this problem, we have let me just, we have a paraboloid. This paraboloid opens downward. And naturally, if you take a vertical plane like x equals 1 and slice the paraboloid, the cut is going to be a parabola. Now, what we want to do is we want to find parametric equations for the tangent line to this parabola at the point 1, 2, -4. Okay, you'll notice that this point here is on the paraboloid. Because -4 does equal 6 minus 1 minus, minus 1 squared minus 2 times 2 squared. Let's make sure of that. Yeah, this is like minus 10, 6 minus 10. That's -4. So you have a point on this paraboloid, and we're gonna, well, and it's also on the plane x equals 1 because the x coordinate on that point is 1. So the parabola on this cut, on this planar cut, we want to find the equation of the tangent line at the point 1, 2, -4. So let's go to the next page. I want to go to the picture first before we go up to the top here. There's a correction. There is a correction here. I was looking at it earlier today. So the point, well, it should be the point. This should be the point 104. So what I've just drawn, and it's not a perfect picture, but the plane x equals 1 is there, and the parabola is on the plane, and the point 1, -24 is down here. So if you go across 1 over 2 and down 4, that gets you to 1, 2, -4. And the tangent, that there's a tangent line that is drawn. And let me see, maybe let's see here, one moment. Okay, there's that tangent line to the parabola at the point 1, 2, -4. And we want to find its slope. Now, one thing we can do is we can say, okay, well, if I were to, go across here and then down here, okay, we have a rise, we have a run, right? So the slope is the rise over the run. Clearly, the slope is very negative. And I'll mention that the highest point, the vertex of the parabola is 4, because you see, if you substitute in, if you think about substituting in, I mean, the equation of the paraboloid is z equals 6 minus x minus x squared minus 2y squared, right? So x is 1, so I put 1 in for x. And then y, you want it to be as small as possible, so you let y equal 0. So that gets you z equals 4, and so the point 104, which is here, is the highest point on the paraboloid. So if you note here, let me just see here what we have here. Okay, that's fine. That's fine. If you think about it, this almost looks like you're going down -8, because you got 4 here down to -4 here. So that's going down -8. And then since this point here is 104, I want to be a little bit careful. Well, maybe the run is like something like +1. At any rate, the slope looks to be like some negative number, maybe -8/1. So how do we get there then? All right, we want the parametric equations for the tangent line, right? So what matters here, of course, is I want to just let me just see here one moment. Okay, so we think this might be -8, but this here, this rise is the partial derivative of z with respect to, hold on here, one moment. It's the partial derivative of z with respect to y. I'm not saying this. No, I'm not saying this the right way. That's not right. No, the slope, if we think of, if I complete this, the slope of the tangent line which, as you know, is this tangent line. That slope is going to be the partial derivative of z with respect to y. Because the tangent line is going in the y direction. It's going that if as you go down the tangent line, you're going, when you go down, you're also moving in the y direction. As you move in the positive y direction, you're going down on the tangent line. So this is the partial derivative that you want. And that slope is, we need to find that slope in order to get the direction numbers for our parametric equations of this tangent line. So we compute the partial derivative of z with respect to y is equal to negative 4y. Well, yeah, that makes sense because remember, z is equal to 6 minus x squared minus 2y squared. So we hold the x constant and the derivative of negative 2. So all we're left is the derivative. All we're left with is the derivative of negative 2y squared. That's negative 4y. And now we're going to substitute in 1 and 2 in there because the point that we're interested in is the point 1, 2, negative 4. So we get a slope of negative 8. So that you have to think of that then as a rise in the z direction of negative 8 and a run in the y direction of 1. Well, this allows us then to get those parametric equations we're looking for, okay, because I mean x is 1, period. But and remember the 1, the 2, and the negative 4, the line passes through that point. Then if the slope is negative 8, okay, the direction vector, okay, is going to be 0, 1, and negative 8. Okay, in other words, the vector 0, 1, negative 8 has a slope of negative 8 over 1. And so that's why over here, I can put a plus 0t. That's why you have those coefficients of 0, 1, and negative 8. Okay, I just wanted to, I wanted to do one like this with you because it's an important problem. And I'll mention the book talks also about partial differential equations. For instance, Laplace's equation that comes up. Well, what I'm trying to say is partial derivatives and second partial derivatives come up. I'll just show that real quick in the ebook. But we're done with this problem. But are there any questions? Are there any questions at all? Okay, let me just then show you briefly the ebook. So everybody had time enough to copy this example down, or give me a thumbs up if you're good. Okay, wonderful. Wonderful. Angela, Matthew, Narina, Yeva, Abdullah, wonderful. Samuel, Alberto, wonderful, wonderful. No, Simon, no implicit differentiation in this example. Very good, Arian. Yeah, this is one though that involves understanding the geometry of the situation, and I thought it would be nice to do one of those with you. And let me just show you here in the ebook. So Laplace's equation, I don't know if any of you have maybe seen this in a class. Probably not, maybe not, but Laplace's equation plays a role in heat conduction, fluid flow, and electric potential. And then there are also wave equations that are based off of these second partial derivatives. So there's a whole course on partial differential equations that we don't teach at Montgomery College. We teach the regular ordinary differential equations, but these partial derivatives will come up later on in engineering applications. So are there any questions? Okay, let me go ahead and stop the recording then, and we are done discussing section 11.3.